Today we will write relations in Haskell. And also we will write some function which determine the properties of this relation. Such as transitivity, reflexivity, symmetry, asymmetry, or some kind of order in partial order, preorder, and so on. Okay, let's start from some mathematical facts. If we have two sets, x and y, we can define the Cartesian products on these sets. What is Cartesian product? To build the Cartesian product, we need to take ordered pairs of the first element belongs to the set x and the second element belongs to the set y. Okay, we create a new set which contain these elements or ordered pairs. Okay, and this is our Cartesian product. After that, after we construct a Cartesian product, we can construct some binary relation over this product. So we can just take some set from this Cartesian product and we will have a binary relation. So actually binary relation is a triple of two sets, x and y, and third element is element g, which is subset of Cartesian product of x and y, called the graph of binary relation. Here we have the x is our domain or set of departure of R, and y is our codomain or set of destination of R. If our x equal to y, then we have the homogeneous relation or end relation. Otherwise, if our x not equal to y, we have a heterogeneous relation. Also, we can define the domain of definition of or active domain of any relation. This is the set of all x such that x relate to y. Of course, this active domain is the subset of the domain. Also, we can define the image or range of our relation or codomain of definition or active codomain. This is the set of all y's such that x relates to y. And of course, our range is a subset of codomain. Okay. Homogeneous relation is phrased as a relation on x. So if our x is equal to y, we can say, then when we define the relation, we can say that our relation, we have a relation on x, or a binary relation over x. Actually, the binary relation is defined by a set of ordered pairs. And also we can look at our binary relation over a set x and y. I have something as an element of the power set of x and y. So if Cartesian products of x and y, if we take the Cartesian product of x and y, and if we take the power set of this Cartesian product, we can say that the binary relation is the element of this result. Now let's start with encoding our relation. So, as I said, the relation is a set. So that's why we need this module here, which represents sets in Haskell. And let's define our relation as a data type, as a type constructor rel. And we need to have two types, A and B, as the parameters, because to define the relation, we need to provide this triple of the x, of the y, of the domain, of the codomain, and of the g, of the graph of the binary relation. So let's use some data constructor here, and define our triple. So at first we need to define the set X, and this and what is the type of this X? So we can define the type of this as a set of type A. But also we have the Y, and we define this second element of the triple or codomain as a set of B. And of course we have a graph which actually represents our relation, and we will also use set here and define our pairs as a type, as a pair type which constructed with A and B. Okay, and let's give some name to it as G. Okay. And let's derive show for this. Show, I think we will need this. Okay, let's run our compiler. So actually not compiler, run GSI and load our file. Okay, and it's loaded. This means that we successfully determine the data type which can encode our relation. After this, I think we need to start from some functions. Let's create a function which takes the image of our relation. So we need to have some relation of A and B as an argument, and we want to produce actual image is a set, and that's why we want to produce a new set of type B. Okay, this is the image. How we can do this? Okay, of course we can take our relation as an argument, and we need we're not interested in the codomain, we just interested in we're not interested in domain, we don't interested in codomain, we just interested actually in our graph, a relation graph. Now we can transfer our G, we can transfer it to list and take all the pairs of this list. We don't interested in the first pair of the just first element of the pair. We just interested in the image in the second element of the ordered pair, and this is our B. And how we construct the final element, we just take our B as it is, and now we can transfer this list to a set with a set from list, I think. Okay, let's try to reload. What's wrong here? I think I need to derive here. Okay. To list, as to list, we take our function from set module. Set from list ord. Okay, let's add, of course, to have a set, they need to add constraint to ordering type class for our B, I think. Yes, yes, it's done. Also, after they do image function, they can create function active domain, which do exactly the same thing, but for our X. So we want to extract the active domain from our domain. Actually, this is subset of our domain. Okay, I think like this, and exactly the same function. We can copy it from here, and we just take A's. No, B is just A's. Okay, like this. Let's recompile, and we use active domain here. Yes, it done. Okay. What we need to start? Oh, we have now our definition and we need to start somehow. How can we start? Of course, we want to construct somehow our relations. And for this, we can define function from list, which will take our list, which represent our set X, and the second list that represent our set Y, and also the third element which represent our graph of the relation G. And this is a list of ordered pairs of types A and B. And we want to produce our relation of type A and B. Very simple. And let's define this function. We have X, we have Y, we have G, and we can write definition. And of course here we can have some problem, which we need to catch the validation. We can be in situation that we define some inconsistent data. I mean by that we can provide here some list of pairs in which the sum of the first or the second pairs not contained in this list of X or this list of Y's. And if there is some elements which are not contained in this list, we want to throw somehow an error which tell us that we have inconsistency in our definition from list. How we can write this? Okay. How we can check the list for empty? I think this is a length function or null function. So, yes, we have null function. We can say that if we have no not in Y elements, so actually this is a list of the elements which not presented in this list of B. If it is empty, if this list empty, or and so if this list empty, and also if empty the list of not in X elements, then we can successfully construct the relation from these lists, because we have the consistency here. Okay, how we construct the relation from the list? We just take these lists, transfer this list to relation for X, and transfer this list to relation for Y, and also we transfer it to relation to the set from G, and this is our new relation. Of course, they do this if this condition holds. But otherwise, if they found some errors errors. If they have some x that x or y that are not in our domain or codomain, they need to throw the error, I think. Let's throw the error here. Error elements not in X, and they will print our not in X. Elements. Okay, and also maybe I don't want to do some nice printing here. I just want to show the errors. If they present, I will show them. And if we have not in Y elements, we show elements which not in Y. Okay. After this, I think we need to define our not in X function and also not in Y function. How we check that elements not in X? We can take our graph, relation graph, and extract the pairs from it and pattern match our A's like this and construct a new list, I think, of these A's. But they need to check the condition that our A is an element of X. Actually not element of X. Okay, of course here they have the list. Yes, they have the list. And similar, exactly similar for our B's. Our B's must be elements of Y. Can be reload. Okay, let's try to fix it like this, I think. LM. Of course, we need to have here equality types for our A, equality constraints for our A and B. Like these, because they do the comparing here with the LM. Okay, we have the also, I think, show. Also, we need to provide the show constraint for A and show constraint for B. And also we need ORD. As I said earlier, we need ORD because they construct in the sets here, and that's why they need ORD. Actually, I can just create ORD. Provide ORD here, and I don't need EQ because if I had ORD, I have EQ. Okay, and we're done. We loaded. Okay, and now I think we can play a little bit of our relations. We can try to construct some relation. Let's provide the x like this and y's like, I think I like this. But let's define the homogeneous relation. They just provide the similar sets. And they provide the relation, actually the relation, like I think like this, something we can provide. Okay, and as you can see, they have this relation. Let's save them, save it, let's give the name to it, and let's take, for example, the image of this relation. As you can see here, we have, no, let's create, let's define here 1, 2, 3, and 1, 2, 3, like this, to have a smaller image. I want to have the subset, not just the whole set as an image of our domain. And now we can check the image. Yes, they can see that they catch the image from here. Also, I can take the active domain. And as you can see, yes, they have this subset which contain only one element. This is 1. What we can also try to provide some errors. How can I provide some errors? What if I put here some element which is not in my element set, and it created? Why it created? No, it's not created because Haskell is lazy, and then I try to construct this error. I have here the exception that we have not element in Y. This is our 7. Okay, and here you can see optimistic is all the X in our X. So actually we do the validation. We can construct our relations now. Okay, now let's take a step back to the theory. Now, we have some important particular homogeneous relations. There are 3 types of this relation, or the set X. The first is empty relation. This is just the relation which has no ordered pairs. The second is universal relation. This is just the whole relation, the most powerful relation which can be created from the X. Actually, this is our Cartesian product. And the second is the identity relation. This is the relation then they have when they pick up all the elements from the X and construct pairs which have the as a first element X and as a second element our X. So actually this is, it has the property of the symmetry, And let's build a function which create this relation. So we can create an empty function which create the empty homogeneous relation, and actually we don't need any arguments for this. We just can define its type as a relation of A and A. We have same A's here because this is a homogeneous relation. How can we define it? Okay, we can define it very simple with a relation constructor, and we can take this part from here actually. We just we have empty. I think we have empty for set. Yes, we can take empty sets, and this is our empty relation. Also, we can build a universal relation. This is but here we need to provide some X. Yes, here we need to provide some list of A's, and they will have the homogeneous relation. But what I think that here we also need to provide this thing. Because I think there is not only one possible triple, then they have empty relation. They have somehow other configurations, then they have some x and y's, but our relation graph actually is empty. Okay, and let's do it in this way. So I will create some set here for my x and set here for my x again. This is y, but this is homogeneous and they are equal. Okay, universal relation. How we construct it? So we need to take out the x and define our relation. Of course, they need to have some x here, and this is exactly the same thing for x and y. But here we need to also generate the graph of pairs. And how we generate this graph of pairs? So we can use a list comprehension here. I think we just take the let's name it xr xs set of x's. So we take every element of this x and build a new pair of x and x, and this will be our relation graph. Okay. Of course, here we have xs. Okay, I forgot what I need. Of course, I need ordering because I construct a set. And here. We done. What I do here? This is not universal, this is identity relation. So I implement the identity relation here. Identity. And universal is our next relation. This is a universal relation, and I think it has exactly the same type signature. But here we need to provide actually Cartesian product. Cartesian product. This is exactly the same thing. And I think one of the simplest ways to construct a Cartesian product is using the sequence function. Okay. So we need to sequence not go in here, because if I use sequence I will have the list of lists, but I need a list of pairs. So I'm talking about that I can create a Cartesian product like this. But here is not a pair, not an ordered pair. And I think this is we can use the lift function here. I need to import some module. Import control applicative. After I have this import. Let's at the moment do this like this. So if I have this lift a2 function, and I can lift the constructor, the pair constructor, into my lists, and this will give me the Cartesian product. That's why I can use it to define this argument of our constructor. And also we need to transfer this to a set. What's the problem? Let's try like this. Okay. Let's check our universal. Universal for 1, 2. Okay, you can see they have the Cartesian product here for our homogeneous relation, and this means that we're done. Okay, now let's start from some properties of the homogeneous relations. And first is the reflexive property. What they have? They have some homogeneous relation of type A and A, and they want to check, is it reflexive or not? Reflexive means that we have this constraint on our relation. And how we can check this? Let's pattern match our relation. They have some x set of x's. They're not interested in the set of y's because it's exactly the same. And of course we're interested in our g. Now g. What we can do here? Okay, I think we can just reverse over all of our x's, and here we need to have some Boolean value which shows that it is that this pair of x and x is the element, or if the work of the sets, we can check the member. This is a member of our graph. Okay. And if all these things are the members of our graph, we can say that this is a reflexive relation. Oh, this is a set member. Okay, here we need they need a list, but they have set, and I can't do. That's the problem. Is set is not a functor. Okay, we can look at this. Set is not a functor. Okay, set is not a functor. I can implement this logic. I think the fold function. So I think I can do something. I can use something like this. So. Fold, for example, fold L. What I need? I think I need to provide some lambdas here which take our initial state and it takes some element x and here we just do the checking that our S is a member of XX, our XX is member of our graph. And as initial value, we need to provide, I think, true. And we need to fold over XS. Okay, I think this should work. Okay, let's add ordering constraint here. We done. Oh, now let's create some relation. We can create a relation using identity function. We can just provide some set. And this is our relation, and we can check that it is reflexive. Yes, it is reflexive. But no, this is wrong, this is wrong, this is incorrect. I think we need to use something like this. But we have all function, which we can use here. Oh, let's comment this part. All function. Let's provide some lambda for this function which takes x and in this lambda we actually need to check the S member. I think we can take it from here and provide our excess relation. Yes. Next property which you need to implement is the symmetric property, and it's defined like this. For all x and y which belongs to x, if x related to y, then y must relate it to x. Okay, let's do the definition. We need, of course, we're interested in our relation, then better match it. I think we don't need x here. What we can do, I think we can use all function again. And how we check it? We need some lambda here, and we need to some foldable. This is our relation graph. What they do, we take for every pair of this graph, they can add and better match this pair as A and B. And what they need to check, we have this A and B relation, and they need to check that we have a member of symmetric member of B and A in our relation GS. Yes. And if all this holds, then the symmetry is holds. I think like this. Let's construct some relation. from list, think 1, 2, 3, and 1, 2, 3, and also from 1 to 2 and 2 to 1. And this is the symmetric relation. Let's check for this symmetric. Yes, it is symmetric, but if we don't have this symmetry case, then we can see that this is not symmetric. But is this reflexive? No, it is not reflexive. We can check this. And interesting that if we have with, for example, 1 and 1, this is not reflexive because we need to, for every element of the X, have this reflexivity. The next is irreflexive or strict relation. For all X which belongs to X, X not related to X. Okay, I think definition exactly like it looks like something in a reflexive way, but they need to just use not here. Okay. Irreflexive. I have bad formatting here. I think I need to remove these things. Okay, we done. What relations check for? We can check for reflexive. For example, this is, yes, this is a irreflexive. But if I add one symmetry case here, you can see that this is not irreflexive because this condition is broken. And what we need to say, they need to wow, that was awesome. We need to say that reflexive and irreflexive are not exhaustive. This means that reflexive is not equal to not irreflexive. For example, here we have this is not irreflexive and also it is not reflexive, as you can see. So this relation. Okay, the next property is antisymmetric property. For all x and y which belongs to x, if x relates to y and y relates to x, this leads us to x equal to y. So you have no two different elements that relates in a symmetry. There is only exist such elements. So if they relates in a symmetric way, this means that they equal. There is no different elements for this symmetry. Okay, let's go to definition. I think this definition is look exactly in this way. So we, of course, they need to provide some lambda, but we have different We use all function, they provide some lambda, and they iterate through all of our pairs. But how we generate Boolean value here? If so, we can generate it like this. If our A is equal to B, then this is okay. We can return true in this case. That's why I will put OR here. Okay, this is OR in Haskell. I don't remember. Let's check this. Yes, this is OR. Or otherwise, if they not equal, I need to check that B and A is a lem of GS. Actually, I need to not check not here. So if they not equal, I must check that B and A is not a lem of my relation. Because if B and A is a lem, this sorry, not a lem, we use member here because they compare our set. Because it is not, if it is not a member, this means that we broke this constraint. So we have, in this case, we have different x and y, and weigh all the members, but they can be only in they need to have only the member for this for different for symmetric elements exchange if they equal. Okay, so I think like this, and let's check this. Okay. Okay, let's put parentheses here. And try to recompile. We're done. And I need to provide some relation and check for antisymmetric case. For example, here, as you can see, they have this broken condition, and this is false. But if I remove it, this symmetry, this is true because we have no symmetric elements with different first and two element. Here, what we have here, the next property is asymmetric property. For all x and y which belong to x, if x relates to y, then not y relates to x. How can they encode this? So this is looks like the previous result, but here I think we need to remove this part of our expression and state like this. So we just go through all the pairs and check that symmetric pair is not the member. Okay. Exactly. We just put this definition here, so very obvious, I think. Let's try to recompile, and we can check for asymmetry. For example, here, and this is false because we have 1 and 1 that's broken. I can remove this 1 and 1, and okay, this is true. This is a symmetric relation. So in other words, the relation is asymmetric if and only if it is both antisymmetric and irreflexive. And that's why I put this definition of antisymmetry here and remove the reflexive case here. Okay, And also, symmetric, antisymmetric, and asymmetric relations are far from being exhaustive. Okay, next property is transitive relation. For all x, y, and z belongs to x, if x relates to y and y relates to z, then this leads us to that x relates to z. Okay, this must hold for all x, y, and z. And we need to say that a transitive relation is a reflexive if and only if it is asymmetric. Okay, pattern of implementation I think will be exactly the same. We need O here, and we need some kind of lambda, a Boolean definition of the result. How we can do this? Okay. Okay, here we pick up some relation, some pairs, some element of the relation A and B. The next thing, we can take all the elements from which contain B as its first elements and relate to some element C, for example. Okay, here I think it is better to rename these things like X and Y according to this definition. So we need to take all the elements which have the Y element as the first element, and they need to pick up this Z element and check that our X relates to Z for every of these Y's. So we need to take all the relations, all the rels with Y. I will give this name relations with Y. So actually this all the elements of X which are related to Y. So actually this is all these, all Z's. Okay. And what they need to check? They need to check that for all again, for all relation of Y, and actually they just can extract the pairs relations from Y. Okay, and now we pattern match these two things like Y and Z and Z, and how we want to build our Boolean value. Actually we want to check that this is that X and Z is a member of our GS. Okay. Okay. I think like this. Yes. Yes. Actually, to simplify this, we can all this condition, but actually no, okay, let's state it as it is. So we can read this expression as all the z which goes from y are related to x. Okay. And now I need to do the last step. I need to define my relations from y. And this is how we can construct this. We can very easy define it. I think we need to provide y here. This is our y from this lambda, and we need as filter function filter. Where is it? There. Yes, they need to provide a predicate and the set. Of course, set our G set, relation graph set. And what we do, we take, we provide some lambda here, we take our x and y. I think there is, okay, y prime, and what they provide some predicate. Actually, this predicate is they need to compare our I prime with our y, and if they equal, when they pick up this element from a set. Okay, let's try to compile this thing. So let's put parentheses here. Okay, it's done. Now we can check our relations for transitivity. Let's check, for example, this relation. Transitive. And it's transitive. Transitive, which or not. Okay, I think it is transitive, but let's provide something that broke transitivity. For example, if I have 1, 2, and I have 2, 1, but I have no 1 to 1, okay? This means that I lose something here in my definition. And of course I have error here. How I find rule from y? I'm not interested actually in this second argument. I'm just interested in equality of x to my y. This is the correct definition, I think. And now you can see that they have false. Here we have true and here we have false. And now if I add from 1 to 1, why this is false? It's false because if I have 1 to 1 and 2 from 1, I have 1 to 1. That's okay. But if I have 1 to 1 and 1 to... I have 1 to 1 and 1 to 2. And I have 1 to 2. And that's okay. Problem is that if I have 2 to 1, and after that I have 1 to 2, I have no 2 to 2. Oh, 2 to 2. Let's add 2 to 2. 2, 2. Okay, in this case we true. Okay. Oh, sometimes it is not very obvious to handle all these combinations. Next type of the property which we want to catch is the connected property or homogeneous relation. For all x and y which belongs to x, if x not equal to y, then must hold x related to y or y related to x. Okay, I think we can try to implement this via all function. Okay, what do they need? We need to have some predicate function expressed as an lambda, which we can and pattern match here and provide some Boolean value. Of course, here we need to provide our foldable graph, a list of ordered pairs. Now, how we generate this Boolean? In the case of x equal to y, this is true. Okay, if x equal to y, nothing to check. We don't need to check these conditions. We can return this true. But otherwise, we need OR here. In this case, if we go here, we have the case with x not equal to y. And here we need to check that LM, sorry, here A and B. They need to check that LM of A and B inside our graph. Okay, or we need to check that LM of B and A inside our graph. Okay, and I think this will be the definition. And now try to check this, that it is worked. Connected. For example, for this type of relation, you can see that this is connected. Okay, this means for every pair, for every different pair, they have holding the relation. For example, for 1 to 2, we have this relation. For 1 to 3, they has. Oh, that's interesting because we haven't this 1 to 3 here. Okay. Of course. I can't take my source of. Oh, this is wrong. Because I need to take all the possible combinations not from GS, from my graph. I need to take it from X, from here. So this means that I need to remove this thing, and here I need to, in this slot, provide some all possible combinations of A and B from X. And I think I can use Cartesian product here. So we have this function in the set model, Cartesian product, and they need to provide two sets. And of course they can, because they have homogeneous relation, they can provide the two sets of X. Let's try. Connected, false. Okay, this is not connected because we have, for example, we need to be connected, we need to add here 1 to 3, I think. And also we need to have 2 and 3. Okay, and this, in this case it becomes connected. Of course it is not very effective. I think if we take combinations it will be more effective, but in this video I don't want to focus on optimizations. I want to just implement the definitions of these properties. Another type of property is strongly connected. This is more strong property than connected. Here we need to have, for all x and y's belongs to x, we need to have x related to y or y related to x. This means that they can take exactly this implementation and remove just one condition, then our elements are equal. In this case we need generate true only if one symmetric case of these elements holds, relation holds for this. For example, AB or BA. Okay. And I think this should work. Strongly connected. As you can see here we have false because they need to add 3 and 3 and it became strongly connected. Okay, the next property is Trichotomous property. How we define this property? Defined if all x and y belongs to x, which belongs to x, hold exactly one of the conditions. The x must related to y, or y must related to x, or x and y must be equal. So only one of these things must hold, other must not hold. One of these 3 things. So this means that I can do the definition exactly like in the previous case, but here I need to, of course, change some condition, and to calculate this condition I need to have A and B, and here I can define it. Okay, we have here some A and B, and how I define this condition. So one of these 3 must hold. So this means that I must have one of these cases. I must have one case. If my A equals to B and A and B is not LM of GS. And also B and A is not LM of GS. This is one case. Or we need to pick up next case. Next case, if our A is not equal to B and x related to y, or y related to x. So we need to choose one of these things, and let's at first check that A and B related, x and y related, and of course we need to check that B and A is not related. We check it here. And the last case, if symmetric to the previous case, if A not equal to B, but here we need to check that A and B not related and B and A related. Okay. And now let's check how our trichotomous work. Okay, some problems. Of course, not equal. We need to express like this. Okay. Let's try parentheses. Try to use parentheses here. And here. And here. Okay, like this. And also, I think they need this here. Okay, done. Let's try to check. Trichotomous. It is not trichotomous. This relation is not trichotomous. Because here, for example, we have this symmetry here, they need to remove it. Let's remove this symmetry. And check now. It is not trichotomous again. It is broken. I think we can try to add free here. Free. Okay, I think it is easier to find this trichotomous relation if we have only two elements. I want to reduce somehow the number of combinations. Let's remove this freeze here. And look at this case. So which pairs they have? I think problem is here. If I have A equals to B, in this case, we don't need to check this. We need to just check that our LM is inside our relation. So I think I can remove these two things. So I just need to check that it's inside my relation. This is the pair, the same elements. And now you can see that our trichotomous relation is true. For example, I can break it by adding here to 1, the symmetric case, and it's broken, yes. Or I can remove one of these relations, and it's also broken. So this is trichotomous relation. So this means that we have trichotomous. The trichotomous means that there is three things, which one of three things which we need to have only one of them. Okay, the next property of the relations is serial relation or left total relation. it defined as for all x which belongs to x, where exists some y belongs to x such that x relates to y. In other words, it can be called as left total relation, and it's somehow totality in a function that for every x you need to the function must be defined. And here for every element, first element of a relation, every possible first element of a relation that inside x, we need to have some y which relates to this x. Okay. Okay, how can we implement this? I think we can use any function for this. Any. Yes, it is exactly like all, but of course, at first we need all. We need all because we interested in the first element of the pair, and for all these elements must hold some condition. We take all the x's, we take first element of the pair, and here we need to have that. Actually, they need any here. We need any pair which starts with the x. This means that we need some lambda here, and here we need to work through all the graph or relation graph, and here we need to extract some pair, and we interested in the first element, I think. And condition which we check that this first element is equal to element which we choose at first. Okay, I think like this. Yes. We can try to recompile. Of course, here I have not pair, I have an element. Yes. And now let's check seriality. Serial, left totality. It is true. Yes, for every of this axis they have corresponding element. But here, if I remove this for 2, we have false because we have no corresponding element for 2. But for every of this, we must have corresponding element. Okay. There exist also two properties which I want to skip. The first is a dense property, which means that for all x and y belongs to x, such that x relates to y, where exists some z belongs to x, such that x relates to z and z relates to y. Okay, and I think this involves some infinities, and I really at this point don't understand how can I model infinite relations. So I will skip this property because I need to think how can we implement, and is it possible to implement it in Haskell, because they have infinities here. And so next type of property, this is well-founded property, This say to us that every non-empty subset of X contains a minimal element with respect to relation. So if we take our homogeneous relation domain and we take every non-empty subset, it must contain a minimal element with respect to relation. What do we mean by? Of course, we need here to define what is a minimal element, and also I think we can have not, but I think we can model this on infinity relations also. Anyway, I will skip this for this video, and maybe I will do some video about well-founded property. This will be some separate video. The next type of relation is preorder relation. This is a relation with two properties. It is reflexive and transitive, and we already do this checking, so we can just use them. So let's define preorder. We can take type signature from here and define our preorder as it takes some relation, and we need to check that it is reflexive and also transitive. Okay. Reflexive and transitive, and let's try to check. For example, here we can see that this is preorder because it is reflexive. It has 1, 1, 2, 2, and it is transitive because if we have 1 to 2, 2 to 2, we have 1 to 2, and if they have 1 to 1, 1 to 2, we have 1 to 2. So as you can see, the transitivity holds here and reflexivity holds. The next relation is type of relation is total preorder, or also called linear preorder or weak order. And it must be reflexive, transitive, and connected. So this means that we can define this total preorder. It has this type, and we can define it. We can take the check for preorder at first, and also we need to check connected property. Connected. So we take preorder and add connected order constraint, and we will have a total preorder. The next thing is partial order. This is a relation what is reflexive, antisymmetric, and transitive. So we can define it like this and like this. We need to have a reflexive property. Also, we need to have antisymmetric and transitive properties. Okay, if these three things hold, then they have partial order. And let's try to reload this and check that we have some relation, partial order. You can see this is partial order because it is reflexive. We have this reflexivity here, And we have antisymmetry, where 1 related with 2, but 2 is not related to 1. And also we have transitivity here. The next type of relation is strict partial order. This is a relation that is reflexive, antisymmetric, and transitive. And we can easily define it like this, holding all the three properties. Okay. Next is a total order, also called linear order, simple order, or chain. This is a relation that is reflexive, antisymmetric, transitive, and connected, and we can easily define it like this. Four conditions must hold. Next relation is a strict order. Strict total order. This type of relation that is irreflexive, antisymmetric, transitive, and connected. Next is partial equivalence relation. This relation is symmetric and transitive. Okay, and the last relation for today is equivalence relation. This is the reflexive, symmetric, and transitive relation. Okay, we can check for this. For example, here. Equivalence relation. This is not equivalence relation because it is reflexive, as you can see. It is not symmetric, so we need to add 2 and 1 here for symmetry. And now it is all conditions hold. This is equivalence relation. Yes. Okay, I think that's all for today. We talk about relations, especially about homogeneous relations, and we catch the properties of these relations. I think in the next video I will do the implementation for heterogeneous relations, and we will find their properties. And also possibly I will do a video about some operations on relations. Okay, guys, thanks for watching. Push like, push subscribe. See you in the next video. Write comments. Bye bye.